School of Management Studies IGNOU presents an audiobook on the course MMPC 005 Quantitative Analysis for Managerial Applications for MBA program. Block 4 Forecasting Methods Unit 14 Correlation.
After completing this unit, you should be able to understand the meaning of correlation, compute the correlation coefficient between two variables from sample observations, test for the significance of the correlation coefficient, identify confidence limits for the population correlation coefficient from the observed sample correlation coefficient, compute the rank correlation coefficient when rankings rather than actual values for variables are known, appreciate some practical applications of correlation, and become aware of the concept of autocorrelation and its application in time series analysis. Introduction. We often encounter situations where data appears as pairs of figures relating to two variables. A correlation problem considers the joint variation of two measurements, neither of which is restricted by the experimenter. The regression problem considers the frequency distributions of one variable called the dependent variable when another independent variable is held fixed at each of several levels. Examples of correlation problems are found in the study of the relationship between IQ and aggregate percentage marks obtained by a person in SSC examination, blood pressure, and metabolism, or the relation between height and weight of individuals. In these examples, both variables are observed as they naturally occur since neither variable is fixed at predetermined levels. Examples of regression problems can be found in the study of the yields of crops grown with different amount of fertilizer, the length of life of certain animals exposed to different amounts of radiation, the hardness of plastics which are heat treated for different periods of time, and so on. In these problems, the variation in one measurement is studied for particular levels of the other variable selected by the experimenter. Thus, the factors or independent variables in regression analysis are not assumed to be random variables, though the dependent variable is modeled as a random variable for which intervals of given precision and confidence are often worked out. In correlation analysis, all variables are assumed to be random variables. For example, we may have figures on advertisement expenditure, say X, and sales, say Y, of a firm for the last 10 years. When this data is plotted on a graph, we obtain a scatter diagram. A scatter diagram gives two very useful types of information. First, we can observe patterns between variables that indicate whether the variables are related. Secondly, if the variables are related, we can get an idea of what kind of relationship, that is linear or non-linear, would describe the relationship. Correlation examines the first question of determining whether an association exists between the two variables, and if it does, to what extent. Regression examines the second question of establishing an appropriate relation between the variables. The scatter diagram may exhibit different kinds of patterns. Some typical patterns indicating different correlations between two variables. What we shall study next is a precise and quantitative measure of the degree of association between two variables and the correlation coefficient. The correlation coefficient. The correlation coefficient measures the degree of association between two variables X and Y. Testing for the significance of the correlation coefficient. Once the correlation coefficient has been calculated from sample data, one is normally interested in asking the question, is there an association between the variables? Or with what confidence can we make a statement about the association between the variables? Such questions are best answered statistically by using one of the two commonly used procedures. They are: number 1, providing confidence limits for the population correlation coefficient from the sample size n and the sample correlation coefficient r. If this confidence interval includes the value 0, then we say that r is not significant, implying thereby that the population correlation coefficient may be 0 and the value of r may be due to sampling variability. Number 2, testing the null hypothesis that population correlation coefficient equals 0 versus the alternative hypothesis that it does not by using the t-statistic. The value of the sample correlation coefficient is used as an estimate of the true population correlation P. It is desirable to include a confidence interval for the true value along with the sample statistics. There are several methods for obtaining the confidence interval for P. However, the most straightforward method is to use a chart. Once R has been calculated, the chart can be used to determine the upper and lower values of the interval for the sample size used. In the chart, the range of unknown values of P is shown in the vertical scale, while the sample R values are shown on the horizontal axis with a number of curves for selected sample sizes. Notice that for every sample size there are two curves. To read the 95% confidence limits for an observed sample correlation coefficient of 0.8 for a sample of size 10, we simply observe along the horizontal line for a value of 0.8, that is the sample correlation coefficient, and construct a vertical line from there till it intersects the first curve for n, which is equal to 10. This happens for P, which is equal to 0.2. This is the lower limit of the confidence interval. Extending the vertical line upwards, it again intersects the second n, which is equal to 10 line at P, which is equal to 0.92, which represents the upper confidence limit. Thus, the 95% confidence interval for the population correlation coefficient becomes 0.2 is less than equal to P, which is less than equal to 0.92. If a confidence interval for P includes the value 0, then R is not considered significant since that value of R may be due to nothing more than sampling variability. This method of using charts to determine the confidence intervals is convenient, though of course we must use a different chart for different confidence limits. For example, 90%, 95% or 99%. Rank correlation. Quite often data is available in the form of some ranking for different variables. It is common to resort to rankings on a preferential basis in areas such as food testing, competitive events, for example games, fashion shows or beauty contests, and attitudinal surveys. The primary purpose of computing a correlation coefficient in such situations is to determine the extent to which the two sets of rankings are in agreement. The coefficient that is determined from these ranks is known as Spearman's rank correlation coefficient R. Practical applications of correlation. The primary purpose of correlation is to establish an association between any two random variables. The presence of association does not imply causation, but the existence of causation certainly implies association. Statistical evidence can only establish the presence or absence of association between variables. Whether causation exists or not depends merely on reasoning. For example, there is reason to believe that higher income causes higher expenditure on superior quality cloth. However, one must be on the guard against spurious or nonsense correlation that may be observed between totally unrelated variables purely by chance. Correlation analysis is used as a starting point for selecting useful independent variables for regression analysis. For instance, a construction company could identify factors like number 1, population, number 2, construction employment, and number 3, building permits issued last year which it feels would affect its sales for the current year. These and other factors that may be identified could be checked for mutual correlation by computing the correlation coefficient of each pair of variables from the given historical data. That is, this kind of analysis is easily done by using an appropriate routine on a computer. Only variables having a high correlation with the yearly sales could be singled out for inclusion in a regression model. Correlation is also used in factor analysis, wherein attempts are made to resolve a large set of measured variables in terms of relatively few new categories known as factors. The results could be useful in 3 ways. Number 1. To reveal the underlying or latent factors that determine the relationship between the observed data. Number 2. To make evident relationships between data that had been obscured before such analysis. And number 3. To provide a classification scheme when data scored on various rating scales have to be grouped together. Another major application of correlation is in forecasting with the help of time series models. In using past data, which is often a time series of the variable of interest available at equal time intervals, one has to identify the trend, seasonality, and random pattern in the data before an appropriate forecasting model can be built. The notion of autocorrelation and plots of autocorrelation for various time lags help one to identify the nature of the underlying process. The concept of autocorrelation is similar to that of correlation but applies to values of the same variable at different time lags. Now let's summarize the unit. In this unit, the concept of correlation or the association between two variables has been discussed. A scatter plot of the variables may suggest that the two variables are related, but the value of the Pearson correlation coefficient R quantifies this association. The correlation coefficient R may assume values between -1 and 1. The sign indicates whether the association is direct or positive or inverse or negative. A numerical value of R equal to unity indicates perfect association, while a value of 0 indicates no association. Tests for significance of the correlation coefficient have been described. Spearman's rank correlation for data with ranks is outlined. Applications of correlation in identifying relevant variables for regression, factor analysis, and in forecasting using time series have been highlighted. Finally, the concept of autocorrelation is defined and illustrated for use in time series analysis. For various examples and illustrations, you can refer to your self-learning material.
We were listening to the audiobook by the School of Management Studies IGNOU for MBA program, course code MMPC 005, Quantitative Analysis for Managerial Applications. Voiceover by Harpreet Kaur. Edited by Savita. Program assisted by Tarannum Jahan and Jagbandhu Jana. Program produced by Dr. Manoj Kumar Singh. This program was brought to you by Electronic Media Production Center of Indira Gandhi National Open University.